No, we're not going to restart. They'll miss a couple minutes worth. Sorry, AMC people. I missed this slide and this slide. So you're catching up quick. 6 key design requirements that are listed in part 14 CFR part 25. So 1, we don't want any false warnings. Why is it so critical we don't have false warnings going on? So you don't inadvertently shut an engine down, so you don't inadvertently divert. You know, there's a lot of reasons we don't want to. So it's actually a specific requirement that false warnings have to be minimized, and there's a few ways we do that. So you see me do this every time I record. I put the lecture on here so I can monitor how the recording comes through. I guess one's to make sure I have audio coming through. So no false warnings. Second, rapid indication location determination. If we get just an indication we have a fire, it doesn't help us much if we don't know if it's in the engines, if it's in the cargo bay, if it's in the APU, if it's in the gear well, or if it's somewhere else on the aircraft. And so not only that, usually we have multiple engines, 2, 3, or 4 engines. So which engine is it in? Which cargo bay, forward or aft cargo bay is it in? What kind of, things like that. Left gear, right gear. We have to have continuous indication as long as the fire is present. Okay, so the indication does not shut off until the fire is out. And that tells us 2 things. The biggest thing there is, so it keeps it in our minds so we know where that fire is or where that smoke is. Okay. It doesn't mean that the full indication is going on. Often these indications are a common messages, flashing lights, noises, right? Audible. It's very hard to think through and make decisions when you have a lot of like noise and blinking lights going on. So it doesn't mean that all can't be shut off. There's a provision to shut that off, but like the engine fire message will stay on ICAS until the fire is put out. And that tells you that the fire is out. So it can tell you if you have been effective in eliminating that threat to the aircraft. Whether it's fire or smoke or whatever it might be. They have to have the ability to check their integrity before flight. What does BITE mean? It's an acronym. Most components and almost every component on a new aircraft has BITE. What is BITE? Typing it in. Airplane BITE. What's BITE? No one? Guess I should spell it out. Built in test equipment. Okay, built-in test equipment. So it has to have a way to check it. And this was even before it was computerized. There were, even the most simple systems, they had ways to check the integrity. Is the system is everything working correctly? And can it detect fire or smoke, whatever it is designed to detect, without having to bring in some kind of outside test device? Because pilots, right before a flight, aren't going to go get a blowtorch and go up to the fire loops to make sure they indicate by heating them up with a blowtorch. So they're not going to go get a can of smoke spray, which is what we use to test fire extinguishers. It's like a fake smoke, and spray it at the fire extinguishers to see if they work. There has to be some kind of built-in test that can be performed. And most of the time it's every flight. It's at least once a day. It depends on the specific item in the airline and what their operating certificate says. Model and that kind of, well, yeah, BITE, yeah. I've seen like, there was a fire test that on some of our airplanes, I've seen where some operators do it every flight and others, they do it just first flight of the day. The 2 airlines I worked at, they ran the same test. Once felt they needed to do it every flight. The other one did it once a day and felt that was enough. I can't remember which one was which. And it has to be damage resistant and tolerant. So even if something gets damaged, we still have to have, some kind of redundancy there, some ability for it to detect, even if the system, every element of the system isn't working perfectly, there has to be some built-in redundancy and damage tolerant design. So there's different types of fire, overheat, smoke detection that we need to be aware of. So overheat detection doesn't necessarily mean a fire, it means things are getting too hot. That's a plane I worked on. That one, not the bottom one, the top one. And I've done that before. They probably did a wet motor, put fuel in the engine without lighting it off, and then someone went and didn't dry motor it to blow the fuel vapor out, and you start it and you blow a fireball out the back. I've had it happen when there was a fuel control issue. It was dumping way too much fuel in the airplane. So, yeah. Rate of rise detection. If we've got an area where things are heating up too quickly and it's going to likely result in something, if we can prevent it to getting to the point of actual ignition taking place, or prevent, heat from building up to the point where it causes damage, if you can catch it while it's rising quickly rather than once it's already got too hot, then you have that. Flame or infrared detection. Not super common on transport aircraft, more of a very common nowadays on like helicopters. They monitor gearbox temperatures with infrared sensors and things like that. Smoke or optical detection, primarily in areas like cargo holds and lavatories. Carbon monoxide detection, minor on transport aircraft, not necessarily because of the engines. Engines really don't have a way, right? We're pulling bleed air off the compressor. The chances of carbon monoxide are slim to none. So why might we need carbon monoxide detection on a transport aircraft? And I'll give you a hint, a cargo transport aircraft. What's that? Animals, I guess cows release a lot of methane or something. I don't know. Nope, not animals. So if you are transporting perishable items, oftentimes they are cooled with dry ice. Dry ice is solid carbon dioxide. And so there are limits to how much dry ice you can carry. If you're carrying a large amount of dry ice, you typically have to have carbon monoxide detection equipment to make sure that that sublimating dry ice, that's the gas it's giving off, which is carbon dioxide, doesn't suffocate the crew. So during COVID, when all the COVID vaccines, thank you, were being shipped, they were shipping them even on passenger airplanes. A buddy of mine flew 777s for United at the time. They built these like coolers that could be strapped into each seat, and they each had dry ice in them. But it was way more dry ice than you would normally carry, especially on a passenger variant of the aircraft. And so they had to have carbon monoxide detection. And then combustible mixture detection, not super common, but again, more of a cargo thing. If you're going to be carrying certain hazardous materials or items that could create a combustible mixture, it's that. There is one area where this is being used. We covered it already. Does anyone remember where that was? Where this system is being added now? Or systems that prevent this? So during fuel, we talked about nitrogen inerting systems or fuel tank inerting systems so that we don't get an explosive atmosphere inside of a fuel tank. And that was after the TWA Flight 800 explosion off the East Coast. It was 747, the center fuel tank ignited. So for fire, we're usually looking at areas like engines, cargo holds, and lavatories. This is fire, can be fire directly or it can be smoke, okay? Smoke in the cargo holds, lavatories, cabins, okay? Overheat is areas like ducting. We talked about that when we did pneumatics. We talked about overheat detection systems. Wings for the de-ice systems or anti-ice systems, cargo hold. And then landing gear, we got to make sure that our gear doesn't overheat because of either brakes getting hot or tires or that kind of thing, bearings going bad. So there are landing gear overheat warning systems. And then that combustible mixture I mentioned in areas like cargo holds. So in overheat, we kind of talked about these sensing elements. Remember I drew the two sensing elements, the cross section? Anyone remember the names of them? We name them after the companies that originally built them. So the drawing I made, we had this. Okay. Try again. There we go. Drawing like this, and remember it kind of had spot, I did something like that. And then we had this, right? One had two, Kitty and Fenwal, there we go. So now Kitty and Fenwal both make both types now. Okay, it's just who developed them originally. Does anyone remember which one was which? We say a Fenwal style loop. Which one? Kitty is the second one, right? This was your Kitty loop. And the way I remember that, oops, nice E, Jeff. The way I remember that is the two Ds, right? Here's your two Ds right here. Okay? So the kitty style is the double. So it doesn't actually look like that. I just made them look like these. Okay. And so this is a Fenwal style. But Kitty makes both and Fenwal makes both. And there's actually other companies out there now too that make them. It's just that's who originally patented each type. So that's what we're talking about with loops here. Then you can also have things like spot and optical. We're going to have some kind of a control, either logic board or computer, and then that's going to feed into different indications in the form of lights, messages, oral. And then that test circuitry, that byte test circuitry, you can see here, there's a test switch and some test circuits here. Okay. So here's kind of some cross sections of those. So we've got a Fenwal style loop on top. It's got the wire conductor, the eutectic salt, Inconel. The outer tube is Inconel. Okay. Inconel is it's a steel alloy, but I can't remember what the major alloying elements are. Anyone know why Inconel? What's the advantage of Inconel? So Inconel is extremely strong. It's very heat tolerant. Okay, it's one of the strongest alloys of steel that we have, and it's corrosion resistant. It's kind of a stainless type. And so that is grounded. The Inconel tube on the outside is grounded. And then the nickel wire on the inside is what's connected, here in this monitor circuit. Okay. And so what happens is, as this eutectic salt heats up, its conductivity will increase to the point where there will be continuity between the nickel wire and the Inconel tube on the outside. Essentially, that nickel wire will see a ground applied to it. So on here, if a ground gets applied to this, that tells the monitor circuit that somewhere along this sensing element, it's gotten hot. Okay. The Fenwal style, the Kitty style, 2 wires. They call it a sheathing. Most of them are still an Inconel sheathing. Most of the time the sheathing's grounded, but in this case, one of these internal wires is grounded. The other one is connected to the monitor circuit. And again, that thermistor material, that eutectic salt, it'll allow, it'll begin to conduct, and it'll put a ground on whichever wire here is the sense wire. So that Inconel being very strong is very damage and break. It helps to prevent it. Now these are very, very skinny. These things are like the thickness of like a pencil lead, maybe just a hair thicker than that. So they can be easily damaged. They're very strong for what they are, but they're still not, they're not massive, right? They're designed to be lightweight, fit in tight areas. So they're very small. So what we do is, a lot of times we have redundancy. We have multiple wires. So here is kind of a diagram of these things built up. You can see there's like a metal tube here. That purely is just a support bracket. So usually you have a metal tube with brackets mounted to it. And then the actual sensing loops here, one on each side, they're running parallel. You can see in the metal brackets, there's these little rubber grommets in there, okay, and these quick release clamps. They call them a bushing. That's so that they don't chafe and vibrate. Okay, keeps them. It isolates them from vibration, prevents them from chafe brackets. If they chafe, they can ground out. And with these run in parallel, under normal operation, the fire overheat detection system has to see an overheat or fire indication on both loops. Why do we do it on both loops? Why not one or the other? That helps to eliminate those false indications. Okay. But at the same time, we have to be able to, we want that redundancy to be there. We want dispatchability to be a concern. Right? We want to be able to fly the airplane even if something isn't working 100%. So what you can do is, if one of these loops gets damaged or stops working for some reason, there's typically a switch. They're typically referred to as the A loop and the B loop. And normally they're in a both position, but you can flip it to just A or just B, and it will only look at one loop. What's the downside of that? What's that? Well, that one could go bad, but hopefully you're not going to fly it that way very long. The idea is it's to get it back, maybe a day or two to get to maintenance. But while you're flying with just a single loop, what's the downside? There's a higher risk of false indication. Okay. So that's why it's allowed for a certain period of time, but not allowed indefinitely. Yeah. So you get an indication. It's usually during that bite check. And then what you'll do is, okay, you got an indication. You flip it to the A, do a test again. Did it work properly? Okay, it's probably the B loop. Flip it to B, test it, or flip it to B and it immediately fails. That tells you it's the B loop. So then you flip it to A, you only use A, and then fix the B loop later on. So that's kind of the indication. A lot of your newer ones now, the computerized systems, actually can tell you which one. And rather than having to manually do that, it can do that flop over automatically, and it can kind of do that troubleshooting analysis automatically. So they've actually eliminated the human flipping between the two loops, and it's all done by the computer system. In fact, you can see the CRJs that I worked on, the 200s, had the AB panel and all that, and all these, and a bunch of test switches, and then the 700, 900, the later variants, where that panel used to be about this big and had all kinds of switches on it. Panel was still that big. There was one little push button in the middle. That was the entire fire test panel and fire control panel. So it did it automatically then, but they didn't want to like redo the whole overhead panel. So they have a giant looking panel. It's got one button in the center of it. It kind of looks goofy. So yeah, you'll see both styles where you can manually do it or where you have to do it automatically. So here is that test circuit again. And so there's kind of two tests that we do on these. One is to check if it'll indicate. And the way it does that, this test circuit typically just puts a ground on that sensing element, on one end of the sensing element, and triggers to make sure you get a fire warning. You get an actual warning. The other way to do it is this circuit right here will look and see if there's continuity on that center all the way around. Okay? Because the idea is if you have these, here's your test box, or here's your box, okay? And it's got wires going, and then you've got a loop right here. And oftentimes they'll be connected in series, another loop here, oops, and then another piece of wire going to another loop here. And then you got some wires coming back here, right? So they'll be connected in series. And so what this will do, to test it, one test is we'll call it a fire warning test. This is that test button. So we push that switch, it puts a ground on it, makes it think that that salt created continuity, and it gives it an indication like that there was a fire. The other way is this box is going to say, okay, can I see from one side to the other? Because then if you get a break in it somewhere, right, it knows that there's a break, or say one of these terminals comes disconnected, right? Can you still sense fire anywhere on that? All this is it's looking for a ground right here, or it's looking for a ground right here. Can I still sense fire on that? If I get a hot spot right here and it shorts the ground, will I get a ground down here? Remember, these have next to them, the other half of the loop is the ground. And you've got the salt in the middle. Between the grounded, either the shield or the second conductor, right? So if this gets hot and I get a short to ground here, will I see a ground down here? Okay. If this one gets hot and I get a short to ground here, will I still see a ground here? Yep. But what happens if that occurs? If I get a short to ground here, will I get a warning? No. So this is monitoring to make sure it has continuity. And if it senses that it's lost continuity from end to end, it's going to give a fault to tell you hey, go figure out why I can't get continuity end to end. It may still work. Hopefully it didn't break in two locations. As long as it didn't, most of the time, if you're going to have some kind of a fault or a disconnect, or it's going to get broken, or a piece of hardware is going to come apart, the terminal bolt or something falls out, it's going to happen in one spot, right? You don't typically have two simultaneous failures most of the time. Statistical likelihood of that's low. Okay. So those are the two kind of things it's looking for. Is there continuity from end of loop to end of loop? Am I able to see a ground if a ground is applied to it? Okay. And that's built in. One other type that's out there is a pneumatic loop system. And so these are, rather than having a loop that goes end to end looking for a ground, here it's basically a pressurized tube. So it's still an Inconel tube. It has a core material that's hydrogen charged, okay? But it's not electrical. There's no wiring hooked up to the core material. It's basically a material that at low temperatures, it absorbs hydrogen, and when it warms up, it releases hydrogen, okay? And then the tube itself is sealed. You can see it's got an end cap here. It's pressurized with helium gas, okay? And the isolator, right? And then there's a switch inside of the end of it. And so what happens is as this heats up, that hydrogen charged core gives off hydrogen. So now you have more gas filling the same space. What's going to happen to that space? Do what? It's going to try to expand. It's inside a metal tube, so it can't expand. So what's going to happen? Pressure is going to go up. So when the pressure increases to a point, it's going to push a switch this way, and it's going to create continuity from, this is essentially a ground, to the alarm, and it's going to tell that there's a hot, that heated up, pressure increased, and it triggered the switch. Now there's a second switch in here. What do you think that switch is for? Going the opposite direction. What do you think we want to know in addition to if you have a fire? What? You'll know it somewhere along the loop. That's about all it can do. What happens if this thing gets a leak in it? Will it indicate a fire? No, if it's got a leak, the pressure won't be able to rise. So it's always got a little bit of pressure in it. If that pressure drops, if it loses that pre-pressure, then this switch right here engages, or sometimes it's a separate one, and you'll get an indication that the loop has failed. It's kind of like when you get a break right here, right? So, or that the tube, the detector has failed. Okay, so it has a low pressure indication. That's usually like a caution, like, hey, your fire loop isn't working. And then it's got, as the pressure gets too high from heat, then it'll give you the actual fire warning indication. Okay, so that's part of that damage, indication by it and test equipment, making sure that the system integrity is good, and not saying, okay, all our fire loops are good because we don't have it, and then realizing that all of them have sprung a leak and none of your fire loops would work, right? So it's part of that built-in test. Spot detectors can be a couple things. One type is a thermal switch. That's your bimetallic switch, open. When it heats up, it bends, hits a ground, closes, puts a ground. Those are typically wired in parallel like we've got here. So if you get a ground on any one of these switches, it's going to send a signal to the indicator light, okay? It's also got a test. If you push the test, that puts a ground on it as well, so you get the indicator light, right? So that can test that the system can sense a ground. Now, it can't test individual switches necessarily for that. That's a maintenance function. Get out your blowtorch or whatever, or a heat gun, and go to each sensor and heat it up till you get an indication, okay? The other style is a thermocouple. What do thermocouples do? When they get warm, what do? They output a very small voltage, right? So it's a bimetallic, two different metals that are junctioned together. Typically, they are alumel and chromel. Again, two steel alloys. But when that heats up, they're going to generate a small voltage. And so we can sense, a small voltage. Now here, that voltage is usually small, so you've got a very sensitive relay that's going to close another switch that's going to indicate an alarm and all that kind of thing. You've got a test thermocouple right here that you heat a heating element, and that puts a ground on it, similar to if one of the actual sensing thermocouples were to. Okay, you can see they're in series, so you can have multiple ones. So that sense relay then operates another relay that activates the alarm over here on the right side. Okay. So a thermocouple system. Okay. So those kind of, the two types of loops with eutectic salt, and then you've got the helium tubes, and then you've got thermal switches, and you've got thermocouples are kind of the four heat detection units that we use on aircraft. Okay. Other stuff that we're going to look for is smoke. So here's an example of a smoke detector. There's two types of smoke detection: light refraction and ionization. Okay. Light refraction is there's a light source inside of it and a photoelectric cell. And they are, I say, smoke disrupts light in a way. Typically, they are put 90 degrees to one another. So you have like a light source and a photocell. The light source is almost like a little type laser style. So the light's kind of going, it really doesn't go anywhere. When smoke gets into the chamber where it's located, that smoke reflects that light and it'll reflect some of it down towards that, or an angle towards that sensor. And so when that sensor picks up flashes of light or reflected light, it knows that there's something in that chamber, likely smoke, that's disturbing the light source, and it'll indicate smoke. The other type is an ionization style. And this uses a small amount of radioactive material, typically, can't remember if it's americium, or I'd have to go look at my NDT slides. I have it in there. But it's a slightly radioactive material with a very long half-life. And essentially what you're doing is you have two charged plates. It's almost like capacitive plates. And when you put that radioactive material in there, that small amount of radiation it's giving off actually allows current to flow from plate to plate. Okay. But if you fill that space with smoke, smoke does a great job of blocking low-level radiation. Smoke works well to block low-level radiation, alpha particles. So that, actually these might be gamma-based, I can't remember. Gamma, or, I don't remember the exact mechanism. Anyways, not super important for our purpose. But the smoke blocks the ability, it blocks those radioactive particles, which prevents them from contacting those two capacitive plates, and that disrupts the flow of current through the detector. And so when there's a disruption to that flow of current, that indicates, that is an indication that smoke is present. Okay. They work well for different things. Light refraction, you've probably all seen, there are some smokes that are very, very almost clear, right? Like clear white. These kind of have trouble picking those up, the light refraction style. Okay. Whereas ionization, it doesn't care what color the smoke is. It doesn't care if it's light white smoke or dark, greasy black smoke, right? So, sometimes they have different purposes for different areas. If you're in like a kitchen environment, a lot of times they try to, I want to say they avoid these because you're really only worried about like the thick black smoke, right? Sometimes you get a little bit of the clear white smoke during cooking. It's not a big deal. And you don't want the alarm going off all the time. But for aircraft, we almost always use ionization because we want to be able to pick up whatever kind of smoke might form. So most aircraft are ionization. If you look at this, what kind is this one? That's ionization. It's got the little nuclear symbol there. I can't tell from the label what source it is there. We also, yeah. No, you probably have these in your house. A lot of your home ones are this style. Nope. It's an incredibly tiny amount, and it's enclosed in it's got an enclosure that contains that radiation. So, and it's a very low level radiation source. So even if you are exposed, the exposure is fairly minimal. And yeah, anyone watch Young Sheldon? Didn't they do a thing where he bought a bunch of smoke detectors one time? Yeah. So, and there had been some stories about people doing stuff like that. I don't know how true they are, but so yeah, that's what we're dealing with. It was the ionization style. But yeah, most of your home, a lot of your home smoke detectors are ionization style. So you've probably handled them before. Hopefully you've changed the batteries in yours. Flame detectors, so infrared or optical sensors. These are going to see the emitted heat. These use a similar technology to those temp sensors, or you got to use like the thermal cameras, right, during environmental control system lab. right? This is that same kind of technology, just more of just that single spot detector. They see the heat emitted from fire or smoldering materials. They also can see the heat being emitted by machinery. So that's what I was saying. These are used oftentimes on helicopters to monitor gearbox temperatures. So you can hopefully catch a gearbox failure before the whole thing goes grenades, right? Because the gearbox is kind of important on the main rotor, especially, kind of. Carbon monoxide, rather than using the little discs with the little dot in them like we do in small airplanes, large aircraft, again, primarily if you're carrying cargo that's going to be use dry ice to keep it cold, you're going to have a box that kind of looks like this. It's just got an open grate, and it is going to sense the carbon dioxide concentration as well as time, right? Because it's the exposure. It's how much how much of the oxygen is it displacing in the air? Is that going to be a problem for the humans that are operating the airplane? And so you'll have these that can provide some kind of a readout. And again, particularly, so those 777s that my buddy was flying, they normally don't have carbon monoxide detectors on board, but they installed a kind of a portable one that they could put the detector in the cabin. It had a little indicator that went up in the flight deck with them. And so if all of a sudden, for some reason, they had all this dry ice off gassing, they would get an indication, so they could basically open the dump valve and suck the air out of the airplane, and then, do what they needed to do, put on oxygen masks and that kind of thing. Combustible mixture detectors, I'll be honest, they look a lot like this. They're basically a box with a grate, maybe a little fan in it, help move air through. They can sense things like oxygen, high oxygen concentration, right? We don't want the oxygen concentration getting too high. That can be explosive. Or fuel sources, if you get fuel vapor, and not just fuel, but a fuel source vapor, so a combustible vapor. But it will not sense if ignition source is present. It's purely looking at is the atmosphere ripe for ignition. So here was that. I was talking about the different test switches. So older aircraft was all this kind of relay and switch based. Newer aircraft, it's going to be done through some kind of a control module, whether it's a card or a computer. And here you can see that's going to put out information. It can do both like analog to turn on things like lights. Now you can see these are 28 volt DC. Oftentimes these run on both DC and AC, or at the very least they run on DC. Why is that? So if you lose generators, you still have fire smoke indication that can run on battery or some kind of an emergency source. Okay. But it can also, then it outputs to like the onboard maintenance computer, or ARINC 429 can be pulled into your ICAS system or ECAM system to be able to provide those indications. And then you'll have multiple loops. So what kind of loops are these? Can you tell? Those are the pressure. Those are helium loops. Right? They got the little switch, high pressure, low pressure switch set up there. And so, but again, the idea is computer going to be hooked to whatever kind of, whether it's something that interfaces with eutectic loops, whether it interfaces with pressure loops, whether it interfaces with spot detectors or thermocouples. That's going to do that. And so most are some kind of a combination with some analog control, some digital. When we go to test these, here's that smoke test that I was talking about. Okay. So the bite test, things for like short to ground, continuity, integrity. Is the computer able to talk to the little circuit board inside the smoke detector or the heat sensor? But there are some times where we do need to do maintenance and functional checks. And so for heat, we'll often use like a heat gun. We're going to use a blowtorch for like a plumbing torch for testing fire loops in lab this week. And then something like smoke check, right? This is a can, this actually comes out clear. It's basically just a clear aerosol, and you spray it at the inlet of a smoke detector, and it makes it, it should set it off just like if it got filled with smoke. And we've got this, we'll test that. We'll test a smoke detector using this stuff. Sometimes we'd use heat blankets as well. But we really didn't do too many actual functional checks besides the smoke detector one we do every now and then. You weren't going out there doing the loops very often. The bite checks caught most issues. For indication, these are almost always going to give some kind of a light. There's like your master caution warning we talked about, right? The light right there on the glare shield in front of the crew. It's going to give an oral warning. It could be a fire bell or a klaxon, or it can be, oftentimes it's a combination. So a lot of your new aircraft, it's going to set off a continuous fire bell, and then the audible dialogue system is going to be like left engine overheat, jet pipe overheat, left engine fire, right engine fire, cargo fire, forward cargo fire, aft cargo fire, APU fire. There's all kinds of things that can be. Gear bay overheat was one of them we had. So it'll have oral warnings, and the newer ones tell you exactly what it is. ICAS or ECAM messages. Old airplanes would just have lights for different areas. Now everything is message-based, right? If you have a central warning system on one of those kind of in-between era aircraft, it'll bring up an indication on there. And then the actual things used to fight the fire, whether it's buttons, pull handles, whatnot, those typically are going to light up to draw your attention to it. So if you get a number one engine fire, you usually have like a fire handle or a push button for each engine. That one will light up, not the number two or the number three or the number four. And that way it draws your attention, hopefully, to the correct spot. And if you have a left engine fire, you don't accidentally pull the fire handle for the right engine and shut down the right engine when your left engine is the one that has the problem. And so by having it light up only the items that you are interested in to fight the fire, it helps to guide your action. These are often going to be guarded and dual action, though. Okay, so it's not just pull the handle, fight the fire. It's pull the handle, twist it to discharge the bottle. Push an arm button, push a second button to discharge. Okay, and a lot of times they have like a guard on them too to prevent it from going. In Boeing's, the fire handles, you cannot actually pull unless there's a fire indication. Or there's a release button you can push to pull the handle. And when you pull the handle, that closes your fuel valves, it shuts your air valves, but it doesn't actually discharge the extinguishing agent. To discharge the agent, then you have to twist it. Okay, but oftentimes we can fight the fire simply by removing the fuel source. So in order to discharge, or in order to put them out, we have our extinguishing things. These can be portable for areas like the cabin, or they can be permanently installed, like this fire bottle shown here. And we need to eliminate at least one of the items in the triangle of flames, right? And they can do this a couple ways. When you discharge material like this, you're doing two things. One, most of the time you're going to displace oxygen. That can be done a couple ways. Halon bottles like this, gas bottles, they basically push all the oxygen containing air out of that space, and they fill it with an inert gas. Okay? Halon is halogenated hydrocarbons. They're a terrible greenhouse gas, but they're a great firefighter. Okay? It's the truth. The other thing we can do is eliminate heat. So a lot of these cool. Some of them, like this gray one right here, this just shoots water. This is used for putting out like paper fires if someone throws a cigarette in the trash can. All you really need is water, and it primarily does it by cooling it. It cools it down to the point where ignition doesn't sustain anymore. Okay? So you can cool it, get rid of the heat source. The third one is fuel. These ones that put out foam or that put out the dry powder, those create a layer at the top of the fuel, and it separates that fuel from the oxygen source. It creates a physical barrier. You've all seen firefighting foams, right? They create the bubbles, right? That is a blanket that separates, say, the fuel spilled on the ground from the oxygen in the air above it. It also has expanding gas. What happens to gas when it expands? It cools, so it's cool. So that's the second thing. So that deals with both. Firefighting foam it blocks the fuel, it eliminates the heat, and it blocks the ability for oxygen to get in there because that foam is filled with carbon dioxide. Right? So it's kind of a three trifecta. Right? This is why you need to, why doesn't water work on oil? Grease fires. Oil floats on the water. So the water goes to the bottom, the oil comes to the top, it doesn't do anything, right? The dry powder that we use is going to sit on top, or the carbon dioxide foam is going to sit on top. And in fact, putting water on an oil fire makes it worse because that oxidizes, or that, not oxidizes, that vaporizes and throws the oil everywhere and atomizes it and causes it to become explosive. Anyone ever seen a kitchen fire demo with water being thrown on it? Yeah, it's because the oil gets thrown up in the air and vaporizes and flashes. Not fun. And hydrogen and oxygen, they break apart into hydrogen and oxygen. That also can be explosive. Okay, so extinguishing agents, halon, people have heard of that. There's a few different types, 1211, 1301, there's a few others, but oxygen displacing, it pushes out the atmosphere. It also it doesn't, but for aviation, it doesn't create a residue. It's non-conductive. It has low toxicity. It really isn't. Breathing halon is not what kills you. Halon pushing oxygen away from you is what kills you. But the actual halon is fairly inert. It doesn't actually really cause major health effects. It's just that it prevents oxygen from getting to you. So, kind of is more of an acute thing. But it's got a big problem. What's this bottom one? So what does that mean for aviation? What is the announcement that you get on every flight you go on? No batteries where? In the cargo hold. That's because your cargo holds typically are extinguished with halon. So those batteries in the cargo hold, actually the halon can react with them and cause it to get worse. If the batteries are up in the cabin, we can see it happening and we can spray it with a dry powder, which doesn't react with them. Okay. Halon is an inert gas. Well, the other inert gas that would work is CO2, but most systems aren't CO2 anymore. CO2 is old school. Pretty much everything's halon nowadays. So inert gases, other types, CO2, other oxygen displacing things. Again, no residue. They provide cooling, right? Because they're an expanding gas, they cool, but they're not as temperature stable. That's the problem. A halon bottle, as it heats up, cools down, the pressure will change a little bit, but not too bad. Carbon dioxide bottles, when they heat up, the pressure really starts to increase inside of them. And so halon, that's one of the big advantages of halon is it's more thermally stable, so you don't have to build as heavy duty of a bottle to contain that high pressure when it gets warm. Okay, what time we got? Yep. Water, talked about that, non-toxic cooling, but it leaves behind water, which can be corrosive. Dry powder leaves residue. It's known as monoammonium phosphate. What do you think the problem with that is? Ammonia and phosphorus are both what? Corrosive chemicals, particularly on aluminum. So they separate the fuel from the oxygen, but we don't use them around aircraft too much because they are so corrosive. Okay, we'll get into the types later. We'll get into portable next time. So I won't release the quiz today. I'll release the quiz on Wednesday after we finish this section of the lecture. So no quiz today. Just make sure you turn in your schematic by tonight at 11:59 p.m.